Our next speaker is Jeff Scargle. He's a research astrophysicist at the NASA Ames Research Center. For the past 30 years, he has pioneered the development of statistical and data analytic techniques for the analysis of time series data in astrophysics. His talk today is on Bayesian blocks, segmented models for detecting and characterizing transients in streaming time series data.
Thank you.
Thanks a lot, and I'm really grateful for being invited to attend this meeting and participate. Really, now is the time for this. This is kind of an overview of a data analysis, a time series analysis method that's been around for a while, but basically there's some new developments, and these are co-authors, co-workers of mine. Jim Chang is in the audience, and this is kind of the outline of a paper that we're preparing on the algorithm and the practical use of it. Today I want to concentrate on just a few parts of this, mostly things that are relevant to data streaming, and I'll end up with, basically I'm just going to make some claims about the use of the algorithm for real-time streaming applications rather than actually demonstrate. And here's the basic idea. The basic problem that's being approached is we have time series data and we want to find a good representation of the variability of the underlying physical process, whatever it is. And these are things that would be nice to have in an algorithm to do this. I won't go through them all in detail, but the key ones are that we want the algorithm to reveal what is real in the data and not what is incorrect or not real. That is, we want to suppress the observational errors and reveal only the statistically significant components of the variability. Driven by simplicity and wanting a generic representation that isn't tied to a specific model kind of leads to a very simple segmentation idea, which is kind of demonstrated in this cartoon. That is, the raw data, whatever data mode it's in, whatever the format of the data is, some sequence of data points. I think of these as cells, data cells. Each one could be an event data, that is the time of arrival of a photon, for example, or it could be a count of the number of photons arriving in an interval of time, bin data, or it could be measurements like radio frequency, flux measurements. And the basic segmentation model is to break the sequence of cells into blocks and to find the optimum such partition of the data cells into blocks. Optimum meaning maximizing some fitness function, some goodness of fit function, which I'll talk about in more detail. And for example, this is just a cartoon to show that even for event data, you can easily construct a cell. In this case, the cell representing the data is essentially a rectangle of width delta t dt, which is essentially the Bernoulli cell size for this one-dimensional case. And the height of the rectangle is 1 over that. So this rectangle tells you where the data was measured and how high it is. And that's all you need in any data mode for each data cell. You can adjust this height if there's some, if, for example, several events happen at the same time, you have the number as the numerator, and you can even correct for, make this into an energy quantity if you want. So what I mentioned the fitness function, what is being optimized in this algorithm? Well, it's some sort of fitness measure constructed by adding together the fitness of each block, each collection of cells, each partition element in the set of cells is called a block, and we want to have some measure of goodness of fit, and the simple model we start with is piecewise constant. So all this block fitness is any measure you want to cook up, telling you how good a constant rate or a constant signal strength over the block is. Examples would be if you're a Bayesian, you might want to calculate the posterior probability for that model given the data in the block. Maximum likelihood, it turns out to be very good such a fitness function. And for any data mode or way of collecting the data, you can easily construct a block fitness function. And block additivity is the key thing. That is, the fitness of the whole model is just the sum of the fitness of each of the blocks in the model. And that typically derives from the statistical independence of the errors of each measurement. So you can see it's a very simple formalism and setup. You're constructing the simplest possible model of a time series, piecewise constant. I always challenge audiences to name a simpler model, a simpler non-parametric model, and no one's ever done it. And if I had a little more time, I could actually prove to you how the algorithm works. This is a cartoon of the kind of iterative approach. Let me just say it's a dynamic programming algorithm. It sounds like a fancy name, but it's a very simple concept. But it's based on a kind of a trick, a dynamic programming trick, invented many decades ago by Richard Bellman, one of the founders of operations research and dynamic programming. And by the way, there's a fascinating story about how Bellman chose the name dynamic programming for this kind of mathematics. It's not what you might think. It has to do with the person who was the Secretary of Defense at the time, who hated science and hated mathematics. But read the story on the web. Anyway, dynamic programming, it's an iterative approach. You basically chew your way through the data. You start with the first data cell and work your way through. And at each step, you're adding a new data point, but you've stored the optimum partition of all of the previous set of data points. And so when you add a new data point, you're not guaranteed that any of these change points or any of these partition elements are the same. But what you do is you consider all possible locations of the beginning of the last block in the optimum partition. And you can easily calculate, it's an order n calculation, the fitness of each of these potential final blocks all the way to the final block being the whole data set. And because of block additivity for the fitness, all you have to do is add the fitness of the last block to the fitness of the previous partition, but you save that from previous calculation. So it all works out. It's an n-squared algorithm. It gives you an exact optimum of this problem. In fact, it's so simple. Here's a few lines of MATLAB code to implement the algorithm. As usual, there are a few tricks, like the cost function is in this log posterior function that hides some stuff. But basically, it's a very simple algorithm. And here's the result on some gamma ray burst data, where the raw data are time tag events, photon arrival times. And the yellow histogram is just an arbitrary histogram. You have, in order to see the data, you kind of have to pick some histogramming, some bit width, just to show what's going on. The optimum partition of this interval, of the data in this interval, found by the Bayesian block algorithm, are the blue rectangles. And you can see it's completely adaptive to the structure and the data. It's not fixed binning. It's like allowing the bins to be adaptive. And where there are statistically significant sharp rises, the algorithm assigns a bin, if you will, to that structure and basically finds all of the statistically significant changes in the data. One comment is, of course, you don't believe that the real light curve is this discontinuous. It's really blocky like this, or it's really represented by a step function. It's an approximation, but that's like anything in data analysis. You never get exact representations. And you may worry about the fact that, well, it's not smooth, and I'm used to seeing nice, smooth pictures, and suppose I want to do something with the data after I've processed it. Am I going to have trouble because of these blocky edges and so on? And in practice, the answer is that's not a problem. Things that you want to calculate from the data, for example, the width of pulses in the gamma ray burst, or the rise time of a pulse, or the decay time, all of the things you might want to calculate in a post-processing step are just as easily, or perhaps more easily, derived from this block representation than it would be from a smoother representation. Here's just kind of a random sample of some applications of the algorithm to data. This is largely Fermi gamma ray space telescope data that I've been associated with, and Jim Chang has done a lot of analysis of this. Here's an example of something I'm going to talk about a little bit more, but in the outline I mentioned that gaps can be dealt with. Here's a gap in the data. I forget exactly which data set this is, but you can essentially ignore gaps and you don't need to worry about them. You just run the algorithm, and two things are possible. Two things can happen at a gap. One is that there can be a block that ends at the beginning of the gap, and then the next block in the representation starts after the gap. Or, as happened here, there's a block that spans the whole gap. What that block is saying is not that I know magically what happened in the gap, it's just saying the signal before the gap and after the gap are consistent with being the same to within statistical fluctuations. So in terms of visualization, you might want to draw a dotted line there, but the point is because you're working locally in the time domain, you don't have to worry anything at all about gaps. You can just pretend they're not there and nothing bad happens. Here's another example of gaps. This is radio frequency data. I think this is from the Owens Valley project at Caltech that Tony Reed and his group are doing. And again, you see that there may be gaps in the sampling, but you don't have to explicitly worry about them because you're operating locally in the time domain. Here's another example. I won't go into detail. This is the fascinating discovery by the Fermi telescope at the Crab Nebula. The Crab Nebula itself is flaring in gamma rays, large these flares. Here's a Bayesian block analysis. I'd like to show this slide because it turns out the search space that the algorithm is searching through is huge. It's 2 to the n. If there are n data points, there are 2 to the n possible partitions of that data set. And in this example, that means there are 10 to the 468 segmentations of these 15,000 and some data points. Obviously, an explicit search would be impossible by any algorithm. But because of that trick, the dynamic programming trick, you're implicitly doing that search in order in squared time instead of exponential time. Here, just I won't go into detail because it's just kind of a minor thing. There's one parameter in this representation. It's essentially a parameter in the prior distribution that you assume for the number of change points, or the number of blocks in the representation. That's the name of this parameter. In a sense, it's a bit like a smoothing parameter, because if you change it, you kind of modulate the number of blocks, and therefore you can get a simpler or a more complex representation, but there's no real smoothing going on here. The edges are sharp, so it's not a smoothing parameter, it's kind of a complexity penalty. And this shows a way of calibrating that parameter against the false positive rate. You just run simulations. These are results for simulations. Each curve is for a fixed number of data points in for the event data, starting from, I think, a few dozen out to a few thousand data points. And this is like a performance curve where the fraction of false positives in noisy and data that's pure noise with no signal drops off as you adjust this parameter, penalizing large numbers of change points. And so you can calibrate. If you pick a false positive rate that you want to accept as okay, then you can find what parameter value to use. And now I'm going to go through an example to show how the algorithm works on multivariate data. Suppose you have several data streams that are different data modes. One is event data, and the other is bin counts, and there's a third one, let's say, which is like the radio frequency data. It's a flux measurement at a few times, whatever the sampling times are. And you may think you have to analyze them separately, but if you want to, you can use this algorithm to make a combined analysis where the constraint is imposed that the change points in all of the different data streams occur at the same time. Now, you may not want to do that. You might want to modify that approach. But assuming that the changes are occurring at the same time, here's a test signal that I just generated arbitrarily. It's two blocks with infinitely sharp edges and then a normal distribution in the middle. And event data would be a set of photons drawn from this probability distribution. And of course, you have the usual problem with how do you display the data. Here's a tick mark at each of the photons. It doesn't tell you much to your eye. So what else can you do? You can bin the data, but this data, then the shape and the structure depends on the choice of the bin size, and you want to avoid that. Another thing you can do is show the cumulative distribution function for the data, which doesn't do any binning, but it's a little harder to interpret. So anyway, there's a little bit of a problem just visualizing this data. But you put those events through the Bayesian blocks algorithm, and out comes the blue representation. Fairly nicely captures the edges of this big block. It misses this block completely. There's just not enough samples there to prove that it's there statistically. It does an okay job with the central peak. So that's just analyzing the event data that I simulated for this case by itself. Here's independent random events, but now binned in an arbitrary number. I think there's 32 bins here. The blue histogram is the data, the green is still the signal. Run the Bayesian blocks algorithm on the bin data, and you get this representation. It's not so good at the edges, and it still misses this block, and it's okay. But then suppose you had a bunch of measurements at randomly chosen times with given errors of this, again, the same underlying process, but independent data. A separate analysis of that data gives you this representation. There's a bit of art in deciding how wide to make the blocks in this plot. All you know is here's one data point and there's another data point. I've arbitrarily made the block edges halfway between the points because it's the simplest thing to do. This, how we captured the second block, okay, because I guess good luck, we happen to have a few points that fell in the block. But you can combine all of these data streams together, and here's just a cartoon of how you do it. You have, imagine this being an n by 4 matrix, where these are the times of the first data series, which in this case is event data. Then you just concatenate that with the times of the bin data and the times of the sample measurements. You then restructure this whole matrix by ordering the times and moving the data points accordingly. So now you can use this, these 3 slices through the data array to calculate the cost function. In a way, the details don't really matter. So it's just a way of combining the data together, adding the cost functions. And here's the result of this joint analysis. The black curve, the 3 different colored curves they're not the separate analyses. They're what the individual data sets would show with the combined change points. But anyway, the thing to concentrate on is the black curve, which isn't terrific. There's a few odd things in it. And I should say this is sort of work in progress, because finding the correct that parameter from the prior distribution, you have to figure out how to choose that for joint data like this, which I haven't quite done yet. 5 minutes, great. Okay, so here's a summary. And I've sort of cheated because I haven't really justified yet the kind of the main point of contact with this conference, and that is, here's a summary, the great things the algorithm can do. Nothing matters in the way of gaps, even variable exposure and multivariate cause no problems. But everything that I've talked about can be easily implemented in a real-time or trigger mode. If in fact, if you understood that cartoon and the MATLAB code, there's just a very simple test at each step in the iteration, which says, have I found a new change point in the data? Have I returned the next significant change point? The algorithm can return, and therefore, in real time, find a transient in the signal. Let me end by advertising a new book that's come out that I'm the co-editor with a group that mostly at NASA Ames, Advances in Machine Learning and Data Mining for Astronomy, and a future conference that's going to be held at SLAC that's on similar issues to things that we've talked about here. Okay, thank you very much.
Do you have any questions here?
Is there an assumption that the variance is somehow predicted by the flux measurements? I know in astronomy that makes sense, but in other fields you can imagine that the change point is only happening in the variance. So you have effectively the same average flux, but then all of a sudden things sort of go wild and blow up variance. So how do you deal with uncertainty in the data? I mean, does that modify the blocking algorithm?
Wow, that's a great question. There are kind of two parts to it. The uncertainty in the data is kind of built into these data modes. The fitness functions that I didn't exhibit explicitly all are based on a statistical model. For example, on count data or event data, the Poisson distribution is explicitly. In fact, the maximum likelihood cost our fitness function is just the maximum likelihood of the Poisson distribution. And in the measurement case, explicitly the errors are included. But the other part of the answer is something that I think is one of your points, which I never thought about, namely treat the variance of the data as the time series that you're analyzing. And I think you could do that. You could input the data as the variances rather than the signal strengths themselves.
Changing, so you can have both the levels changing and the variance.
Right. The whole point of sort of the abstract formalism behind this is to make any sort of data mode possible, and that would be an interesting extended data mode where the variance was part of the variability that you're looking for. But all you have to do is figure out what to define as the fitness for a block and plug it into the algorithm. That's very good.
So Jeff, basically what you have is a data transform of sorts.
Right.
And so the question is, are there some classification methods for which this would be an optimal representation?
Well, possibly. This is not unrelated to an approach to classification that Eamon has used in his work, and I don't know if he's still in the audience. His original classification scheme was something like, it was a segmentation representation, a little bit like Bayesian blocks, but yes, you could imagine doing a classification based on the block structure. It contains all of the correct variability information. You'd have to do some work to fit it into some sort of machine learning algorithm, but that's a process.
Any other questions? Oh, follow-up from Jeff.
No, it's a separate question. Sorry, this is cool. No, I'm not sorry it's cool. I'm happy it's cool. Sorry I'm dominating the mic. So if Is there a way to ask a statistical question about was there an event at this time, or is that essentially implicitly being asked? So if you go back several light curves, what you wind up seeing is that you've got a bunch of blocks, and my eye tells me there was some sort of event that happened where you thought there was nothing. If I then say, oh, well, somebody from another telescope told me at that time there was something happening there, can I ask, after you've made this block, a statistically rigorous question of what's the probability that there wasn't a change there as well?
Yes. Yeah, you could do two things. One is you could get this other data and put it into a joint analysis. But what you could also do is two things. You could go back and change that parameter to make it have the false positive rate higher and maybe find something that would be statistically valid because you knew a priori where to look, so the trials factor would be different. And you can also calculate the errors of the representation. It's a little tricky because it's not simple. You want the errors for a whole curve, not the errors for a number. So asking the question, what are the errors, you have to say what you mean by that. But yeah, the answer is yes.
Anything else? All right, let's thank Jeff again.
Thanks a lot, and I'm really grateful for being invited to attend this meeting and participate. Really, now is the time for this. This is kind of an overview of a data analysis, a time series analysis method that's been around for a while, but basically there's some new developments, and these are co-authors, co-workers of mine. Jim Chang is in the audience, and this is kind of the outline of a paper that we're preparing on the algorithm and the practical use of it. Today I want to concentrate on just a few parts of this, mostly things that are relevant to data streaming, and I'll end up with, basically I'm just going to make some claims about the use of the algorithm for real-time streaming applications rather than actually demonstrate. And here's the basic idea. The basic problem that's being approached is we have time series data and we want to find a good representation of the variability of the underlying physical process, whatever it is. And these are things that would be nice to have in an algorithm to do this. I won't go through them all in detail, but the key ones are that we want the algorithm to reveal what is real in the data and not what is incorrect or not real. That is, we want to suppress the observational errors and reveal only the statistically. The implementation model is to break the sequence of cells into blocks and to find the optimum such partition of the data cells into blocks. Optimum meaning maximizing some fitness function, some goodness of fit function, which I'll talk about in more detail. And for example, this is just a cartoon to show that even for event data, you can easily construct a cell. In this case, the cell representing the data is essentially a rectangle of width delta t dt, which is essentially the Bernoulli cell size for this one-dimensional case, and the height of the rectangle is.
Our next speaker is Jeff Scargle. He's a research astrophysicist at the NASA Ames Research Center. For the past 30 years, he has pioneered the development of statistical and data analytic techniques for the analysis of time series data in astrophysics. His talk today is on Bayesian blocks, segmented models for detecting and characterizing transients in streaming time series data.
Thank you.
Components of variability, driven by simplicity and Wanting a generic representation that isn't tied to a specific model kind of leads to a very simple segmentation idea, which is kind of demonstrated in this cartoon. That is, the raw data, whatever data mode it's in, whatever the format of the data is, some sequence of data points. I think of these as cells, data cells. Each one could be an event data, that is the time of arrival of a photon, for example, or it could be a count of the number of photons arriving in an interval of time, bin data, or it could be measurements like radio frequency, flux measurements. And the basic